As McMurdo said, I work with Dr. Brittany Schmidt here at Georgia Tech, and we do kind of three-part science. So we're NASA P-STAR program, which is about 50-50 science and engineering development for kind of solar system and ocean world exploration. Nock gave a good introduction to ocean worlds in the first talk of this session. I'm going to dive into that a little bit deeper. But we can also do a lot of climate science, and the analog environments that we work in, Antarctica, are kind of relevant for some of the terrestrial work as well. So that said, here you can see this is the edge of the Ross ice shelf. And after a couple years working in Antarctica, this is the first time I saw this just this past, I guess it was November. So it was pretty wild. It's about a 300-meter thick chunk of ice. So the part that's sticking up here is about 30 meters or 100 feet. And this is kind of the system that we're interested in studying as an analog for ocean worlds in our solar system. What are the processes that are going on below the large ice sheets on Earth, and how good are those as an analog? What are the limits of habitability in sort of non-photic oceans? So all right, backing up a little bit to ocean worlds. So the planets and moons that have oceans. This kind of breaks our understanding of the habitable zone a little bit, because most of these places are places that are not within the sort of nominal habitable zone where you go Venus to Mars for our system, or some of the exoplanet systems. A lot of them are out by Jupiter or Saturn, and they're moons of main planets too. So these are environments that we're really interested in for our solar system that are not kind of in the traditional habitable zone. So Jonathan Lenine, 2017, he wrote a great kind of review paper on what a lot of these bodies are and some of the processes that are affecting them. This is one of the tables that summarizes it. We can focus on those that are extant here. That means that there's good evidence for places that have currently habitable environments or oceans. So the reason that this is possible outside of the habitable zone is from a few different mechanisms. So one, you just have your remnant heat of formation. So 4.5 billion years ago or so, these bodies form, and they've been cooling off ever since. Radioactive decay in the interior from radiogenic elements, that's another way of just constantly generating heat. But really interesting, and for most of these bodies, because they're moons and they're orbiting their host planets in slightly eccentric orbits, this tidal dissipation. They're basically a stress ball that's getting squeezed as they spin around in these eccentric orbits, and that frictional heating actually provides enough heat to keep a lot of these places liquid. So moving on to that, yeah, these are the ones we're interested in. Europa, Enceladus, and potentially Titan. Titan's a little bit more complicated because of the pressure regime. There's kind of a weird sandwich of ice, ocean, and methane on the surface and all kinds of strangeness. There's some people here who work on that. But we're going to focus on kind of the simpler model where, like Earth, you have a rocky core, you have an ocean layer, and then an ice surface. So we'll look at Europa as an example. Again, kind of the structure. Nock talked about this a little bit. And then moving on to a zoomed-in view of that. This is from the Europa lander SDT. NASA is currently trying to think if that's a good idea. Sending a lander to the surface of Europa is something we can do in the next decade or so. But yeah, so Nock talked about how we know there's an ocean there from a lot of the magnetometry data. And we think that this ocean layer, this brine layer here, the salty layer that's conducted is what's driving that observation, and that's our good evidence for that. But above that, you have a crust of ice. Ocean maybe 100 kilometers thick, we don't really know. Maybe a total length or thickness of water layer, ice and ocean, of about 140 kilometers or so. And then people are really interested about what's going on the seafloor. Where are the reductants? Where are the oxidants coming from in this system? Is this something where you could have life? What are the limits of habitability in ice-covered ecosystems should they exist on other planets? We use Antarctica as an analog to ask that question here. All right, go manual. Maybe not. I seem to have broken it. Okay, we're back, maybe. Yeah, so my personal research goals are to characterize both the physical processes and the biology underneath ice shelves in Antarctica, and look at the intersections and how these things interact, and what controls both biological systems can place on the physical systems, and the physical systems place on the biological systems, in terms of looking at where the habitable environments are distributed and where things might live. And then take that, extrapolate it to Europa and other systems like that to guide and provide context for where you might best want to land on Europa or look for in the ocean. Look for habitable or biosignatures in the ocean. So again, in Antarctica, some of the processes that we're really interested in is this depth, temperature, and salinity dependent ice flux. Because as ice is moving around underneath, it's entraining organics. It's controlling where things can live at that ice-ocean interface. And that's a process that's likely ongoing at Europa as well. And that can control where organics are getting incorporated into the ice shell, where you might want to land with a lander. We look at bathymetry, baseline topography. It's also kind of an unconstrained thing. It's really hard to get observations underneath these ice shelves. This is actually a report from the 2014 Ocean Observatory, something like that, symposium, I think. And they're like, well, how can we understand these problems? Usually we drill a hole, we put a mooring down, and we can get like kind of 1 point measurement of what's going on. But we're trying to expand that a little bit so we can understand the bathymetry and the topography and the processes on a broader spatial scale. And then from that, how are we controlling the habitable niches? We have a few early observations of life underneath this ice shelf. The Ross, for example, is 1,000 kilometers wide. So there's life under there, and it's not entirely clear what's powering those ecosystems, so we're trying to understand that. The community makeup, what microbial systems are providing the sort of the base of the ecosystem. How does that change from the open ocean to the back of the shelf? And where are these nutrients coming from? And then what from that can we apply to ocean worlds? So this is kind of our field site. We do a lot of field work. It's mostly field work, actually. This is Antarctica, the Ross Ice Shelf. About 1,000 kilometers from the northern edge at the bottom here to the top. The stars are our field sites. We do most of our work right about here by McMurdo Station, which is the largest U.S. base, next to the New Zealand base. This is another site about midway, and then finally a site at the grounding zone where the ice goes afloat. So an ice shelf is a sort of a floating glacier. Probably should have started with that. But again, we're interested in how things change from the photic ocean, where you have photosynthesis driving a lot of life, to the currents that might be dragging some of that detrital material underneath and powering ecosystems, to sort of all the way back at the base of the ice shelf, how things are surviving back there. We know there's life back there. So again, that gradient. Okay, so field data, what do we use to do this? We've built an underwater vehicle here at Tech. It's 12 feet, 3.5 meters long or so. It's a very small diameter. We designed it to fit through boreholes because it's very hard to drive in from the front of the shelf. You can't get very far. So we've kind of got this like have robot will travel model, or anyone who's doing a climate study on Earth, they're putting a borehole in, putting a mooring in or something like that. We can also go along and deploy the robot and increase the science return. We've got some standard sensors here. So in the front we have sonar, helps us not run into things. CT is conductivity and temperature, proxy for salinity and temperature. DO, dissolved oxygen. We have some camera systems, some lasers for scale, get us scale in the imaging systems. And then we've got kind of a science module here. Side-scan sonar for mapping the seafloor. CDOM, which is dissolved organic materials, which kind of helps you understand communication with the open ocean. PHORP, which is interesting if you might try to find a hydrothermal vent or somewhere where you have a disequilibrium of compounds coming out of the seafloor. Turbidity, also good for hydrothermal systems detection. And again, cameras, laser scales, lights, etc. So it's designed to be modular, and we also have some people at Tech that are helping to develop sensors for future ocean world exploration, like cell counters or holographic microscopes, and using IceFin as a sort of a payload carrier for that. Okay, so this is kind of what that looks like from the surface. This is out next to Erebus, which is one of the larger volcanoes in Antarctica. We've got our little, called the A-frame here. It's just an aluminum structure we built. Drill a hole in the ice. The hole's right down there. And then IceFin will hang from here and then dive down below. We've got these little tracked vehicles here, which is kind of how we get around the ice, and generators, tents, etc. And this is what that looks like underneath the water, which is kind of cool. So here you can see we've got our lights on, so we're recording some science data here. We've got side-scan sonar running. We use a fiber optic tether for live data recovery, because of course you can't transmit, other than acoustic signals, you can't really transmit data very, very well through water. And then this is what another way we can get some data. We can just go out on snow machines, drill some holes. This is my advisor here, Dr. Schmidt. And she's got, we call this Cassini. It's one of our lab's most productive sensors. It's a CT sensor that we can just take wherever we go, drop it through the ice, similar spot, and then we get kind of those point profiles. And really, what we're trying to do is understand those environments, cross this gradient, and then tie that back to the processes that are influencing the biology that can be present there. So, starting from the front of the shelf, where we do, this is kind of where the station is, and then this is an overview of all the historical observations that have gone on underneath the Ross Ice Shelf, for example. So here, we've got a lot of our work out at the edge as we're kind of tuning up our systems and practicing. ANZ, that's the Antarctic New Zealand program. They just put a borehole in 2017. They're collaborators with us, just a couple months ago. The Ross Ice Shelf project, that was a massive effort in the late 70s to put a borehole in. People were really curious about what's going on in these ice shelves. So they went down, they found some fish and things like that. And then next year, we're going down with New Zealand, or actually, excuse me, I think we just bumped this back to next year. So we're going to wait one more year, but then do some drilling at the grounding zone. and kind of expand our observations of ice bin. And so this process of how water is moving and where ice is melting at the base of the shelf or accreting at the base of the shelf really controls what kind of biology we observe. So at the front, you can see there's kind of platy crystal textures. You have things like amphipods that are hanging out in the water column, and they're filter feeding off of material that's coming in from the open ocean. That's probably not our best analog for an ocean world. It's not really a photic biosystem that's providing that kind of material. But the ice is something we're interested in. So 1977, they go down, they find fish 500 kilometers from the open ocean. It's kind of surprising. Not a lot of food there for them. What are they eating? And then 2015, the Wizard project, they drilled at the grounding zone. It was the first time. And they also found fish, which was even more surprising. So they were pretty shocked by that. You would think that most things, if it's currents that are carrying it in, it'd be pretty munched on by the time it got all the way back. Not a lot of carbon left for larger kind of macrofauna. And so we're trying to, again, break down that system. So we're wondering, is there subglacial input of we know there's a lot of subglacial lakes, subglacial hydrology. That's a thing we've known about for just about a decade now. There's meltwater and active drainage underneath the Antarctic ice sheet. Are there methane seeps or vents, hydrothermal or serpentinizing systems underneath the shelf? That's been found at Larsen B after the Larsen B ice shelf collapsed. They went in with a ship, a lot easier when there's no ice, and they found just the whole seafloor was covered in microbial mats that were using methane as their carbon source. And then, of course, the sort of the easiest one is, it is enough. It's enough carbon coming in from the open ocean. Yeah, so from the biological observations to the physical controls, back to the same diagram, but now we're going to put some data that we've collected on it. What we're interested in is kind of this 1, 2, 3, 4 process, where you have water that's moving around in the system and it's driving where ice is melting and accreting. So in a polynya, which is where you form sea ice, that's kind of this region here, you're freezing out the freshwater component and rejecting the brine component, and that brine makes the water more dense. The water sinks. The funny thing about pressure and water, being such a weird compound, is as you increase the pressure, you decrease the freezing point. And that's going to be the most important thing driving this here. So as you move water around and move it up and down in the water column, you're either going to melt ice or make ice. So what you do is you move this down, and this is at the surface freezing point, which is about -2 for most ocean water salinities. As you move it down 500 meters, 1,000 meters, all of a sudden the freezing point is about -2.5, almost 3 degrees Celsius. And that means that the water you have is warm, -2 degree water, relatively warm versus where you are. So when that water influences or interacts with the bottom of the shelf here, if where the freezing point is much colder than that water, it's actually melting the bottom of the shelf. But then that meltwater adds fresh water. So you had really salty, dense water. Now you're adding fresh water. That increases the density, or reduces the density. And so now your water is floating back up. It's buoyant and starts to come back up. The opposite happens with the freezing point, and now all of a sudden that water is relatively colder than the depth that it's at, and that makes it super cooled. And so if you have super cooled water, you can start to freeze ice. It's like if you ever put distilled water in the freezer and take it out and knock the side of it, that kind of thing. And so we found that there's kind of a difference in patterns, and you can observe these using the conductivity and temperature sensors that we have, and you can draw these profiles. And you can characterize the water based on the freezing point. So the top here is the temperature of the water in Celsius. So if you draw the freezing point here, draw the temperature here, you can pick out, ice shelf water. That's this water that's coming up, that's super cool, that's below the freezing point. Or the high salinity shelf water, that's relatively warmer on the right-hand side of the freezing point compared to the high salinity shelf water that's coming here from the surface, from the polynya. And you can track that as you move back from the shelf and start to understand the water properties that are driving ice accretion and ice melt. And then from there, start to get at the processes that might be really relevant for ocean worlds. Okay, so this is one quick example of some stuff we can do. I went ahead and put a video in a PowerPoint presentation, which is always risky. It seems to be working, it's very simple. Basically, this is a dive track where we're tracking the vehicle's position as it goes underneath the ice. And on top of that, I can lay all kinds of data from the other sensors that we have. I can look at trends in dissolved oxygen, trends in dissolved organics, trends in redox or pH, and all kinds of things like that. And from there, start to make 3D maps of these environments, which is a pretty good step ahead of the 1D kind of mooring observations. Yeah, so that's what I've got for today. Thank you very much. I want to thank, it's NASA-sponsored work, but there's no way that any of that happens without the NSF, the United States Antarctic Program, and our New Zealand collaborators. Thank you.
Thank you, Justin. Any questions?
That was a good talk. What do you envision for the technology development for undersea communication on the scale of Europa Ocean?
Yeah, that's an excellent question. I think that's kind of the biggest question right now in terms of, this is obviously a very long-term thing. You want to explore the ocean and ocean world, or into the ocean of an ocean world. That's like a 75 to 100 plus year kind of timescale in terms of the hardware development. And the communication and the data relay from the ocean to the surface, when you're trying to get through multiple kilometers of ice, is a crazy problem. So people are working on that, but it's not clear exactly what the best way to solve it is right now. On Earth, it's a little bit easier, and we can do things with both optical and acoustic modems. So optical data in water, if the water is very clear, you can do it with pulse lasers and get actually pretty good data rates, but you're limited to just a couple hundred meters, so not really good for the scales that we're looking at here. Acoustic, you can do a bit better, but of course your frequencies are different, so your data rate is a little bit lower. But you can get acoustic kind of through if you have like nodes that can amplify the signal as you go, you can get a couple kilometers, amplify it, a couple kilometers, amplify it. Of course, it's dependent on the temperature and salinity. You need to know the profile of the water column to know your sound speed very well. So you need a little bit of data ahead of time to figure out how exactly to do that. But one of the technologies that we actually use for localizing the robot underwater, because you can't use GPS. GPS makes it like this far through water or ice. Not great for the depths we're trying to go to. Is acoustic and long baseline transponders that you basically ping and use that to triangulate. So yeah, I think acoustic technology will really be the way forward, and probably there's talk of like a robot that melts the ice shelf and drops off like little pucks behind it every couple kilometers that are acoustic modems and amplifiers to get data back. Because it'll be a one-way trip for the robot whenever you go to an ocean world, but you need the data back. That's a good question, thank you.
Hey Justin, so earlier you were telling me how you're about to go to another expedition to Antarctica. You've been preparing for that. So how's your strategy different for that, and what are some of your goals that might be new? I mean, it's a different time of the year, so.
Yeah, sure. Yeah, so generally when you go to Antarctica, you go in the summer, which you might guess, it's a bit nicer, and the sun's up. It's pretty easy to work there actually, 24-hour sunlight. This year, we're actually integrating a 4K camera system, so we're pretty excited about that. We're going to get some really good imagery from the seafloor. We did a couple of sites last year that we want to return to underneath the Erebus Glacier Tongue, which is kind of like a sort of a miniature ice shelf. Do some practice work and get to the grounding side of that. It's a big ice stream that's coming off of the side of Erebus right next to base, so we can drive there in the day, kind of do day trips there, and practice doing some of the acoustic observations and sonar observations that we want to do at the grounding line of the Ross. So we're excited about that. What else are we working on this year? We've got some collaborators at Tech that are building us some sensors. We have a microfluidic system that's supposed to eventually hopefully measure cell counts in real time, which is very interesting. So that's Nick Speller and a couple other guys at Amanda Stockton's lab. She's, I think, in chemistry, but also has an engineering background. And then we just got a postdoc, Andy Mullen. He's going to be working on a digital holographic microscope, which is over my head, but basically, my understanding is that is a way of measuring particle volumes kind of in 3D space as you're transiting with the robot, again, in real time. So some of that sensor development that we're pushing for future ocean worlds, kind of like a Picasso, Matisse, Cold Tech sort of thing. We're excited about testing some of that stuff out this year as well.
Wow, cool. That's very interesting. Thank you.
Yeah, thank you.
Are there any more questions? Okay, so a few questions. First one, as far as bathymetry, why not just use radar above the ice as opposed to attaching a sensor to the equipment?
For what question?
We're trying to map it underneath the ice, I guess.
Trying to map underneath. Yeah, sure. So it's a very good question. One of the first projects that I worked on was called Simple, and that was an A-step project, which you're probably familiar with. Josh has worked with Brittany a bit in the past. And that was Don Blankenship is the PI of Reason, which is the radar sensor on Europa Clipper. It's supposed to launch in the next 5 years or so, hopefully. And we designed that entire project, or a large component of it, to look at the ice from underneath to sort of ground truth the radar from above. The radar works great until you introduce salt into the problem. So you use the radar to kind of get structure of the ice and define the ice-ocean interface, but as soon as you hit any kind of conductive fluid or conductive material, you lose all of the radar power. And so you just kind of fade off into nothing. So it's very hard to get like a unique solution for your radar if there's brine in the situation. So what we're doing with the underwater vehicles is basically mirroring the flight. So the Reason instrument, again, also they use Antarctica as an analog. They would do overflights and get a radar profile of the ice and the ice shelf from above. And then we kind of try to match that radar profile with the vehicle from underneath and use our sonars to look up and get the thickness and the concentrate or the composition and the overall texture of the ice from below and use it as kind of like a ground truth for the radar. And from there, you can get some of the context and some of the information that you need to interpret those radar results when you can't do that. So when Reason goes to Europa, hopefully this work will give us a little bit better idea of how to interpret the bottom part of those measurements there. With any luck, going to give us the thickness of the ice shelf. It's a good question.
That's really cool. Thank you. One other question.
Yeah.
So the picture you showed us of underneath the ice at the interface, you could see the sun shining through. How deep do you have to go, and can you go that deep underneath this ice shell to, I guess, get away from the sunlight to try and see what kind of biology would be there without something that might feed on?
Yeah, so that photo was under sea ice, which was probably about 1.5 meters thick. The ice shelf, the McMurdo ice shelf, which was a smaller side section, it's about 20 meters thick, and that's totally aphotic. I'd say maybe upwards of 10 meters of ice, normal, kind of mostly fresh ice. Anything thicker than that, you don't have really much light left to drive photosynthesis. The Ross ice shelf is anywhere from 300 meters to 1,000 meters thick, and it's not even the thickest in Antarctica. It's the largest spatially, but the Amory ice shelf is like upwards of kilometers thick. So, yeah.
Thank you.
Okay, let's thank Justin again.